Hello, everyone, and welcome to tonight's stream. And I'm just getting set up here real fast, and then we're going to begin. So today we're doing 3.6, and I am going to be doing the reading first, and then afterwards we're going to be doing the questions. So let me just get all that set up here. All right, and so this is the Book of Proof, 3rd edition, Richard Hammock. Download the book in the video description. It's free. It's in the Creative Commons. It's a very nice book. I have a physical copy. You could also get a physical copy if you want. And the answers in the back of the book. I only do the odds, and that way we don't damage the integrity of the book as a teaching resource. So if you want to know if I'm getting something right or wrong, you can just look it up and you'll know before I do. All right, let's get into it. All right, 3.6. That is on... Okay, Pascal's triangle and binomial theorem. Page 90. Okay. There are some beautiful and significant patterns among the numbers n choose k. We now investigate a pattern based on one equation in particular. All right, so let's just write down this particular pattern. So we have n plus 1 choose k, which is equal to n k minus 1 plus n choose k, okay? And we're going to say for any integers n and k with k being greater than or equal to 1 and less than or equal to n, okay? To see why this is true, notice that the left side, n plus 1, choose k, is the number of k element subsets of the set, say, 0, 1, 2, 3, up to n, which has n plus 1 elements. Such a subset either contains 0 or does not. The n choose k minus 1 on the right is the number of subsets of A that contains 0, because to make such a subset, we need to start with the 0 and append it to the k minus 1 number selected from the 1, 2, 3. And there are n choose k minus 1 ways to do this. Also, the n choose k on the right is the number of subsets of A that do not contain 0. For it is the number of ways to select k elements from 1, 2, 3, 4 through n. In light of all this, equation 3.3 just states that the obvious fact that the number of k elements subsets of A equals the number of k element subsets that contain 0 plus the number of k element subsets that do not contain 0. Having seen why the equation 3.3 is true, we now highlight it by arranging numbers n choose k in a triangular pattern. The left-hand side of the equation 3.3 n choose k arranged in a pyramid with 0 choose 0 at the apex just above the row containing 1 choose k, with k being 0 and k equal to 1. So with k equals to 0 and k equal to 1. Below this, a row listing the values 2 choose k for k, 0, 1, 2, and so on. Okay, so it goes like this. 0 choose 0. It's okay if some of this doesn't make sense right now. We will get there. Okay. Two. Okay. I'm not gonna. Basically, this goes on for just on and on. 3 choose 1. I'm going to do one more row after this to illustrate the point. So yeah, so then this row is going to be the 4s. 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. Okay? And then, you know, it goes from next row will be 5 choose 0 through 5 choose 5. 6 choose 0 through 6.6. All right, and then what this does is this creates this following pattern. Okay, and then it just goes on and on. Okay, so yeah, make sure we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay, I guess we can just add the 5s here, so we have an even number of them. 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. Okay. This is called Pascal's triangle. Any number n plus 1 choose k for 0, with k being greater than 0 and less than n in this pyramid is just below between the two numbers of... So, let's see here. So this right here, this outer row, is referred to as n choose k minus 1, and the other one is going to be plus... One second here. And n choose k, I believe, in the other previous row. But the equation 3.3 says that n plus 1 choose k is equal to n with k minus 1 plus n choose k. Therefore, any number other than 1 in the pyramid is the sum of two numbers immediately above it. Okay. So that is the same number like that. This is a really neat pattern. This pattern is especially evident on the right. Figure 3.3, where each n choose k is worked out. Notice how 21 is the sum of numbers 6 and 15. We didn't do that row, but it's the same idea. So just like 10 is the sum of 4 and 6. 5 is the sum of 1 and 4, and so forth. This arrangement is called Pascal's triangle after Blaise Pascal. Probably butchering that. Blaise Pascal. Yeah, I'm pretty sure I'm saying that wrong. It's funny. I have a book by him, actually. But I have not touched it in a while. Huh. Okay. I'm going to keep rolling along here. Oh, Pensées. Thoughts by Blaise Pascal. In the Franklin Library. It's right in front of me. Okay. Continuing on. After Blaise Pascal, 1623 to 1662, a French philosopher and mathematician who discovered many of its properties. We've shown only the first 8 rows, but the triangle extends downward forever. We can always add a new row at the bottom by placing 1 at each end and obtaining each remaining number by adding 2 numbers above this position. Doing this in figure 3.3 gives us a new bottom row. By the way, just as a thought, as like a philosophical thought here, they haven't fully explained to us why this works, but in principle, you could make your own conditional triangle, I suppose, where you make the rule that like the subsequent number has to be the double the two numbers above it or something like that, and then that can be your own condition that you can create, and maybe there would be some purpose to that kind of triangle. But yeah, it works because the rules specify that each subsequent line is the sum of the two numbers above it. All right, continuing on here. Okay, so all right, so we're adding two numbers in. So the number, let's see here. Any n choose k can be computed this way, and by this way, that means is what we do is we take the numbers, and so for instance, well, let's see here. We could always add a new row at the bottom by placing 1 on each end and obtaining the remaining number by adding the two numbers above its position. What this would do, now they showed us what 8 looks like for a choose k, and yeah, and then without having to use a formula, just because by working our way down, you know, we know what the next number is going to be here. This is going to be 20, for example. This is going to be 6. So like just by the rule that you have to add the 2 directly above it to create the next line. Or yeah, and then that's how we populate the line. Now, the very top row containing only one of Pascal's triangle is called row 0. Row 1, so this is row 0. That's row 0. Row 1 is the next one down, followed by row 2, then row 3. Thus, row n lists the numbers of n choose k for 0, with k being greater than or equal to 0, but less than or equal to n. Okay, so now, n choose k, which is equal to n over n minus k. For each k that's greater than or equal to 0 and less than or equal to n. In other words, the kth entry of row n of Pascal's triangle equals the n minus kth entry. This means that Pascal's triangle is symmetric with respect to the vertical line, though it takes through its apex as evident. Okay, so now, all right. Then we have the binomial theorem. In the binomial theorem, this is what we're doing is we're going to write the Pascal's triangle, but with coefficients of x plus y to the nth power. So, basically, we're taking this right here, this, and then we're going to multiply that times x plus y to the nth power. So, the first one, the 0th row, if we do that, remember this is the 0th row. In this case, n refers to the row. Okay, so if we go with taking the 0 row, x plus y to the 0th power is equal to 1. Okay, so we got that. Okay, so and then if we're gonna say next row here, row 1. Let's say x plus y to the first power is equal to x plus y. So we're going to say x plus y, like that. 1x plus 1y. And the next row is going to be like this. X plus y squared. Now, if you remember, if you square an x plus y, you're going to have x squared plus 2xy plus y squared. Okay, and then and that's exactly what we get here. Xy, and we're going to have y squared, and we're going to have x squared for the ones. So that works out. And so the next one is going to be here. So let's say x plus y to the third power, and that's going to give us x to the third power plus 3x squared y plus 3xy squared plus y to the third power. And again, so we have xy squared plus, there we go, x squared y plus xy squared plus y to the third power plus x to the third power, and so on and goes. Okay. That's really cool. That is really useful. I could already see how that's useful. All right, continuing on. Notice that the row n appears to be a list of coefficients of x plus y to the nth power. So yeah, we just demonstrated that. In fact, this turns out to be true for every n. This fact is known as the binomial theorem. It is worth mentioning here. It tells us how to raise a binomial x plus y to a non-negative integer power of n. Cool. Yeah. So yeah, like for instance, if we have x plus y, and I wanted to raise it to the fifth power, right? So, I mean, we could write it out, x plus y times x plus y times x plus y, blah, 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 blah. Or we can write out Pascal's triangle real fast, and then we're just going to say, and we're just going to fill it in. We're going to say x, and then we're going to say y, and we're going to say x, y, and then, except that the only thing is that, let me check this, they're all going to say fifth power. So this is going to be fifth power, this is fifth power, and then, I'll show you, let's see here, let's see here, if I'm doing this right or wrong. Give 1 second here. Yeah, that's right. So in this case, okay, and then what happens is, in a minute. Right. It's a little different. So well, the last row, we're going to say 1, 5. I need more room. I'm going to say 1, 5, 10, 10, 5, 1. And we're raising it to the fifth power. So on the outside, x to the fifth, y to the fifth, right? And then we're going to say, we're going to step in, and then we're going to continue with the x. Say x to the fourth, y, and then we're going to step in. It's going to be x to the third, y squared, and then we're going to step out. It's going to be x squared to the y third, and it's going to be x to the y fourth, and finally x to the, and then y fifth. Yeah. Yeah. So notice that how the x walks across. X to the fifth, x to the fourth, x to the third, x to the second, x to the 0th, which is 1. y walks the other way. Y to the 5th, y to the 4th, y to the 3rd, y squared, y to the 1st, and y to the 0th power. And it just walks across. So any number, really, we can take it, and as we populate the Pascal's triangle, and we walk each time our powers, we walk one way. You know, like we are in row 5, or it could be row 7, and then we're going to go 7th, x to the 7th power, x to the 6th, x to the 5th, walk it all the way down till we get to the 1, and at that point, the 1 is x to the 0th power. And then we walk back the other way. We take y to the 7th, y to the 6th. Now we're walking, instead of from left to right, we're walking right to left. And we beautifully can populate any arbitrary size. All we got to do is just recreate the Pascal's triangle for our own purpose. Really, really cool. Now that, I'm surprised that works. But that is very useful. I could definitely see that being useful. Like if you had to expand on a large number, you can just, well, I guess you could look up what the Pascal's triangle is for that size and then populate it that way. But I'm guessing that that's how calculators work. They probably use some form of Pascal's triangle. All right. All right, now we're going to continue, and then we have the binomial theorem. So basically, yeah. Now they have the whole binomial theorem written out here, but basically the way I described it makes more sense to me. And it's just like, if you want to, you can just try to write it out. But generally speaking, you want to know what is your... well, actually, let's write it out, and then we'll just go over it, because it is worth pointing it out here. Okay, here we go. Okay, so we are 3.6. All right, so basically, binomial theorem. If n is a non-negative integer. Okay. There, in the integer set. Okay, so we're going to say x plus y to the nth power. We want to know what the nth power is. We're going to say, like, to the 2nd power. N to the 0th, x to the n, plus n to the 1st. Now, see, whenever I said you walk it across, the next x is going to be less. And then you're going to have y to the 1st, plus n to the 2nd, x, and minus 2. Y squared, y goes up, plus n choose 3, yeah, x and minus 3, y goes up 3, and then we're going to say plus n choose n, y to the n. And choose n, y to the nth power. So yeah, basically, y grows from left to right. Y goes this way. X goes this way, right? The powers of x. So we're going to say y to the 0, y to the 1st, y squared, y third, and x goes the other one, and then y to the nth power. And x is going to be the other way around. right, we have x to the nth, and then we're going to say comma x to the n minus 1, comma. So again, instead of writing x minus 1, let's just assume that it's going to be right here. So we have x to the 0, x to the first, x squared, x to the third, x to the nth. So that's how they grow, basically. All right. So, they're giving us an example. Let's see if I can just solve this here. Let's say, so we're saying this thing. They want to know what is 2a minus b to the 4th power. Okay? So, Pascal's triangle, 2, 1. So this is 0, 1, 2. And it's going to be 3, 3. And it's going to be, it should be 1, 1. It's going to be 4, 1, 6, 4, 1, 2, 3, 4. Okay. And then we're just going to populate it. So we're going to say this is x. This is y. So we're going to say x is equal to 2a. Y is equal to negative b. Okay? And then we're going to take the Pascal's triangle that I just made here. We're going to say x. What is x at? All right. We have... Right. The x in this case is going to be here. The last one, by the way, remember, it is, in case you're wondering, what is the final one right here for the x? It's the row. You take, it's the 4th row, so it's going to be, it's this power right here, basically. So we have 2a to the 4th power, and then we have the y is to the 0th power, so we're not going to worry about that. And then we're going to say the next one over plus we have, I'm going to say here 4 times we have here. Okay, oh, that's right, because we're using powers. It's not that simple. It's not. Okay, here we go. 4 times 416. 4. Oh, it's 2. 2 times 2 is 4 times 2 is 16 times 2 is 32. Okay, so that means the next one is going to be here. So we got the first one. The next is going to be a to the 3rd power, a to the 3rd power, and then the 2 to the 4th power. In a minute here. Yeah, that should be correct. Except the 2 though, there's a power drop on whole numbers. Okay, let's actually just let's write out just the a's, and then I'll figure out the 2 situation in a minute. A to the 3rd power, and then we're gonna say Let's say, oh, okay, I think I got it. 4 times 2 to the third power. That makes sense. Okay. And then we're going to say, and then we have the b here as well. But we'll come back and do the b's next. Next is going to be a squared and times 6 times 2 squared. And then we're going to have 4 times 2a. And finally, it's going to be to the first power, so it's just going to be here 1. Right. So the a, we have decomposed the a. And then going back the other way, it's going to be times negative b to the fourth. And then we're going to say, I'm going to use negative, plus negative b to the third, plus negative b squared, plus negative b to the first, and then plus 1. Okay, and then let's clean it up a little bit. This was 2 to the fourth power also. So we're going to have 16 a to the fourth power plus, so we have 2 to the third power, which is 8, times 4 is going to be 32. And we're going to have it a to the third power times negative b plus, that's going to be 6 times 4 is 24 a squared. And we're going to square the negative b, so we're just going to call that b squared. And then over here we have 4 plus, we have 8a negative b to the third power plus negative b to the fourth power. Okay. So let's make sure that this worked. All right, let's, and then there's, make sure the numbers match up. 16 a to the fourth power, 32 a to the third power times, all right, so negative b, and they wrote in the book here negative 32. So the negative, you can carry it out afterwards. That's fine. As long, see what happens is, of course, as you should know, powers, the negative number, if it's an odd number, it retains its negative. And we have 24a squared b squared. Whenever you square a negative number, you get a positive number. And over here we have let's see here, then we have a, again, a, negative a, sorry, you can write negative 8a b to the third power, or I kept it in the parentheses. I kept the negative b to the fourth power in the parentheses. Technically, if you wanted to finish cleaning it up, we can do that. You just spread out the negatives. Finish that. I guess that would be neater. So if you do something, you have to apply to the whole equation, just as a rule. Otherwise, it makes something look incomplete. So either leave all your negatives in parentheses or spread it out across the equation. Okay, and that's what we did here. We spread this out across the equation. All right, that was our Pascal's triangle. Let's just do that. Oh, sorry, binomial theorem via the Pascal's triangle. Cool. All right, well, that was pretty fast. Now, we are now going to do the questions. Okay, number 1. Write row 11 of Pascal's triangle. Row 11. Okay, and so I suppose I could either write the whole thing out, or I could start with n choose 0 through n choose n. Well, let's do that. Let's do the other part, because I can always write an arbitrary large Pascal's triangle, but then that becomes tedious. So let's just do n is equal to 11, and then we're going to go with 11 choose 0. Let's say 11 choose 1, 11 choose 2, 11 choose 3, 11 choose 4, 11 choose 5, 11 choose 6, 11 choose 7, 11 choose 8, 11 choose 9, 11 choose 10. Starting to wonder if the writing the whole thing might have been the easier option. 11 choose 11. Okay, so we know that these two are the same. As long as I get to the first half, so every time I answer the 11 choose 1 and then 11 choose 10 is going to be the same thing, right? So let's do that. So we have 11 factorial over 1 factorial with 11 minus 1 factorial. So that comes out to 11 factorial over, let's do that. That comes out to 11 times 10 factorial over 1 times 10 factorial. We're going to scratch that. So that's 11. So now notice right here, we have our 1 here and we have our 10 right here. So that wave fills that in. 11 and 11. Okay. So the 11 choose 2 is going to be the same thing as, and we can just fill it in right away. We're just going to say the next one is going to be 11 times 10 times 9 factorial over 2 factorial 9 factorial. We can just take here and here. We know what the combination, what the split's going to be, right? Which should make sense because we're subtracting this number from here, so automatically it gives you the other end of it. Okay, so now we scratch the 9s. The 2, we're going to scratch that. It's 5. It's 55. That's 55, 55. Okay, so now we're going to say 8 factorial. Hang on a minute. I have some kind of an issue just happened. I want to make sure there's nothing significant going on here. Let me just review the stream real quick. Okay, so make sure everything is still up and running. Okay, yeah, I appear to be up and running. I had a disconnection. Yeah, but everything's fine. All right, now continuing on from where I left off. we have 11 times 8 factorial over 3 factorial times 8 factorial. So this is 6. We're scratching that. We're going to split the 6 into a 3, 9. We're going to be making that. No, sorry. 6 is going to be a 2. A 2, so we're going to take, well, it's going to be 3 and 5. So what we did there is with the 6, we took the 2 out of the 6 and we reduced the 10 to a 5, and we took the 3 and reduced the 9 to a 3. So we have 5 times 11 is 55, and then we're going to multiply that by 3. So that should be 165. Yeah. All right. Okay. Next, we have 11 times 10 times 9 times 8 times 7 factorial over 7 factorial times 4 times 3 times 2 times 1. So I split up the 4 factorial to make it easier to reduce this. So we're going to take the 4 and the 2, and we're going to get rid of the 8, and we're going to get rid of the 3 and turn the 9 into a 3. So then we have 30 times 11. So that's 330. Okay. And then we're going to take 11 times 10 times 9 times 8 times 7 times 6 factorial over 6 factorial. And then the 5 factorial, I wrote that in there, but I want to show you what we're going to do with that. 5 factorial, I know for a fact, is 120. So then what we're going to do is, let's see here, we're going to lose the 10. And we're going to reduce this to 12. And then let's take, all right, let's get rid of the 12. We're going to make it 3 times 4. And we're going to take the 4, turn the 8 into a 2. Yeah, that's fine. 9 was going to be a 3. That's fine. Yeah, I'm going to be okay with that. All right, so now we have 6 times, and these get scratched, so that gives us 11 times 6 times 7 times 6. All right, so we're going to say 36 times 7 times 11. Okay, so that's going to be 2772, 2772. Okay. All right. Let's see if I did that right. Okay, 1, 11, 55, 165, 330. Okay, I was wrong. It should be 462. So, I did my math wrong. So, let's figure out where I did it wrong. 6. Okay, so 5 factorial is 120. Okay, I lost the 10. Let's see that one more time. Let's see what we did. 11 times 10 times 9 times 8 times 7 times 6 factorial over 120 times 6 factorial. 120 is 5 factorial. And we're going to scratch that. And then we're going to scratch that. So now... we have... minus 33 times 4. Oh, okay, right. There was an extra 6 that there wasn't supposed to be that 6. There we go. Yeah, I see that now. That explains it. So it just should have been 11 times 6 times 7, so we'll call that 66 times 7, 462. That makes sense. Okay. Okay, so yeah, except for my math mistake, then the system works. And again, I could have just written out the whole Pascal's triangle, but I wanted to make it work like this because this could be arbitrarily large, right? I mean, someone can say, well, I want to know the 50th one, right? And that would be tedious, right? Because we did 11. No, but it wasn't like terrible. Imagine writing 50 rows of the Pascal's triangle. Now that I would think would probably be more tedious. Especially because we only had to do half the work, right? We only had to get to that point because it's mirrored. So realistically, it looks like we did 11, but the truth is we did 6. So what would you rather do? Would you rather do 6 of the... what are these things even called? Sorry, my brain is just not working. Or K permutations, isn't it? Yeah, there's just yeah, just K permutations. What's the specific one that we're using here though is called the yeah. Anyway, the permutations formula that we're using, we only had to do 6 of them, and to get 11 rows done, which isn't bad. Really is not that bad. And even then, we didn't really have to do 11. We didn't have to do 6. The first 2 are given to us in a sense. We know that 11 to the 0th power, or any, like 50 to the 0th power is going to be 0. And we know that to the first, or 50 choose 1 is still going to be 50. So, because that refers to our singleton subsets. So we have a 50 element set, and how many singletons are there? Well, 50, of course. So yeah, so then the only ones we really had to do was the 4. So we got 11th row by only having to do 4 equations. That's cool. All right. Now let's do this. Okay. Right. Use the binomial theorem to find the coefficient of x to the 8th power, y to the 5th power, and okay. Okay. Of x to the 5th power, y, x to the 8th power, y to the 5th power, and x plus y to the 13th power. Okay. So let's see here. Right. Well, so we need to get x to the 8th. So we have to do okay. Right. So the coefficient in this case, what they're saying is that they want us to know what the whole number is, of course. So let's do that. In other words, we need the row of the 13th row of the binomial theorem, and then we're gonna fill in till we get to the x to the 8th, y to the 5th power. So in other words, we would march, x would have to march 8 steps to the right, or y is 5 to the left. 6 technically, because the first one is 0. Okay, let's do it. We're gonna say, let's see here. Ooh. Let's say we're gonna say 13, choose 0. That's gonna be 1. 13, choose 1. That's gonna be 13. 13, choose 2. 13, choose 3. 13, choose 4. 13, choose 5. So, now this is mirrored. So, we would, from the y perspective, it would be the same thing. So even though I'm marching from the x, I can actually jump here if I wanted to. Because 13, choose 5 is the same thing as 13, choose 8. There. Yeah, that should be right, because that's 8 steps. So yeah, and that's fine. Actually, what I could have even done, I could have just foregone this whole thing and just wrote 13, choose 8, because we know that that is our x. X is to the 8th power. So let's just figure out 13, choose 8. All right. So we have 13 times 12 times 11 times 10 times 9 times 8 factorial over, we have 8 factorial, and then times 5 factorial. Yeah. 13 minus 8 is 5 factorial. Right. And then, so let's scratch the 5 factorial. Let's make that 120. And yeah, we're going to say that's going to be 120. Scratching that drops that. Scratching the 12 drops that. So that's gone. Scratching the 8 drops that. So we have 99 times 13. So it's 13, 11, 9, and as I like to think of it, 13 times 99. All right. And that's going to be 1287. So that should be our correct answer. I believe it's going to be 1287 x, let's see here, x to the 8th power, y to the 5th power. I think that's the answer. Let's take a look. Yep, 1287. Ayo. Okay. And then, what does it say here? Use the binomial theorem. Wait a minute. Right. Except, okay. Oh, geez. That actually, the question 2 and question 3, I was actually answering question 2. Yes, the answer is correct for question 2. In regards to question 3, this is what threw me off, is because they're both in the 13th row. All we got to do is, we don't have a y there. Y is equal to 2. So all we got to do there to solve this one, technically for us, for question 3, is going to be, we're going to say y to the 5th power. Okay, so let's see here. I don't know my binaries as well as I should. 32. Okay. So that's going to be 32 times 1287 x to the 8th power, and then we're going to multiply that out by 1287 for 1184 x to the 8th power. That should be the correct answer. All right. Let's see here. By the way, if you're following along, you could be looking at the results in the back of the book. You can know before me, but it's much better to actually try doing this yourself. Yeah, that's the correct answer. All right, but this is like so cool. Just think about that, right? We can get the coefficient. That is to say, we can get this number right here or that number right there of an arbitrary point of a this is what the binomial theorem is. Okay, that makes sense. So yeah, so we can get that, and then if we know what our x and our y's are, we can solve it. Wow, this is really powerful stuff. Okay, let's keep going. Oh boy, here's a proof. Use binomial theorem. Okay. Let's see here. Use binomial theorem to show sigma. Okay. From n to k. N choose k is equal to 2 to the power of n. The sum of all n's of n choose k is equal to 2 to the power of n. Okay. That's how am I going to show that? All right. Well, if n, well, let's say I don't know. Let's try 2 choose 2. Let's see what that's going to do. That should be 2 factorial. Okay, so that's going to be 4. A minute. That's just 2. 2 factorial. A minute. 2 factorial over 2 factorial times 2 minus 2 factorial. So that's 0 factorial is 1. 2 choose 2 is just 1. So and if we did that, 2 to the power 1. Okay. Okay. All right. Yeah, this is a proof. I can't prove the binomial theorem, unfortunately. We're gonna have to see how they did it. As I say it, there's no shame in looking at proofs. Just because, like, I want to keep this thing rolling along, and if I don't get it like right away and it's not like easily explained, then I can be here for 4 days. So, let's see what they did it. observe that 2 to the n is equal to, oh, okay, hold on. So 2 to the n is equal to 1 plus 1 to the n. Okay, so then, all right, well, let's just, okay, you know what? Let's just use the, I still don't know how I would go about proving it, though. I can grow the Pascal's triangle from here and say that if this is gonna be, let's see here, if this is 3, 1 plus 1, 2, so that means there's 6. Zero, 1, 2, 3. So, what if it was 4? To the n, what is that, 32? That should be 16. Right, okay. So, the only thing I can say that I'll give this a shot. 2 to the 0 is equal to, we're going to just draw the triangle here, 1. And then we're going to say 1 plus 1 to the 0th power is going to be 1. Anything to the 0th power is 1. Then we're going to say 2 to the first, no, lower. 2 to the first power is going to be 2. And then 1 plus 1 squared is going to be to the first power. First power is going to be 2. And then over here, we're going to say 2 squared is going to be 4. Is this breaking down already? Wait a minute. This may be breaking down. My idea is not. Oh, no, it's working. It's just not the way I intended it. It's supposed to recreate the whole triangle. That's what's going on. Give me half. Okay. It's going to be 1, 1, 1, 1. Okay. 2 squared is going to be 1, 2, 1. And then 1 plus 1 squared is 4. It's 1, 2, 1. 2 to the third power is going to be 8. So that's going to be it's going to be so we're going to do the triangle. 1 plus 2 is 3, and 3, that's 6, 7, 8. And 1 plus 1 to the third power is 8, so that's going to be 1 plus 2 is 3, 1 plus 2 is 3, 1, 1 is 8. 2 to the fourth power is 16. And then we're going to just do it from the inside. We're going to say 3 plus 3, or 3 plus 3 is 6. 3 plus 1 is 4. And then we have 1. So that's 4, 1. And then 1 plus 1 to the fourth power is 16. Again, we're going to say 6, 4s, 1s, dot, 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 dot. Okay. Yeah. I don't know. It's not a proof. It's a demonstration. To be honest, doing something like that, because of the hint they gave us, maybe could work. But this wouldn't be considered a proof in the true sense. You can do a million examples, but example by itself is not a proof, because you have to prove that this applies for an arbitrary length. Because, I mean, how am I supposed to, I say, well, it could carry on, but we don't know, right? We don't know. With a proof, So that's why proofs are very hard. Even with everything we've done, oh man, proofs are a whole nother level of difficulty. All right. So we'll just leave it at that. Okay, use binomial theorem to show okay, see, we have 7 and 9, use binomial theorem to show is equal to 0 for any and choose k is equal to for 3k for the sum of n choose k is equal to 0, right? 3 to the power of k is n choose k is equal to 4. Let me see if this is one they're going to offer some kind of proof. Okay. All right. So I'm looking at 5 and 7. See, like something like this, I'm gonna be honest. This is and there's gonna be questions in this book that I just can't answer to a level where I think I'm answering it correctly. And then when we start doing proofs, like they will give us like hints and stuff, and it's like, am I answering correctly? This is the kind of thing where you actually need a professor. And like I said, I haven't passed this class yet. I'm gonna be taking this class. So 5 and 7 are in the same vein. So instead of 5, it's going to be 1 plus 4, and like that, So and then we're going to say 1 plus 4 to the power of n. So like, or 2 plus 2. So yeah, those are the kind of things, since they're basically the same kind of thing. And again, I'm not convinced because I hadn't done a proof. I simply did a demonstration here, but really, like, to say that, yeah, I don't know. Well, this is the kind of thing that maybe as we move forward in the book, if we have when we start doing proofs, they might like give us a fuller breakdown, then maybe we'll do it. But it's nothing to really worry about right now. It's more like to get a feel for how the binomial theorem works. But yeah, pretty much. Let me see here. Okay. So the questions in this section, if you're interested, you really should talk to a professor. Like, I can calculate the binomial theorem to a specified line, like I was able to do it in the first couple of questions, and find the value for that. But to show that it holds for an arbitrary length, not even sure how to show that correctly. So I know maybe a little I don't know, not what you'd expected, but hey, that's just the way it goes with math. Anyway, what I'm gonna do is wrap it up today. If when I take this class, I go back and talk to my professor and get the kind of answer, get this thing answered, what I'll probably do is I'll do like a follow-up video. So for now, I'm just gonna call this, like what it is, chapter 3.6. But after I talk to professor, figure out how to do this properly, then I will make a follow-up, like a 3.6 time, -2, and I will append it to the playlist. So at that point, you can go back and watch that. But for now, I don't want to just like put something out and not be convinced that I answered it correctly, and then just put it out as the correct thing. So that's what I'm saying. Let's just call it a day on this chapter, and I will see you in the next chapter. And look forward my addendum to this probably in about a month and a half. Okay. Until next time.